Good to see you all here. Thank you so much for coming out to see this talk and for coming to PyData in general. It's been a really cool conference so far. I hope you've enjoyed it. My name is Philip Semanchuk, and I'm going to talk to you today about connecting Python with foreign languages. A little bit about myself before we get started. I'm a software developer. I've been doing it since maybe the 80s, something like that. Started off working mostly in C and over time transitioned into different languages and have spent the past maybe 9 years or so working almost exclusively with Python, but I still sometimes dive into C and other code like that, compiled code. And I get to work with a lot of different technologies, web technologies, databases, et cetera, et cetera. I'm a freelancer, so I get to bounce around from company to company and work with lots of different projects and situations, which I like. It keeps a lot of variety in the job and makes things interesting. And so maybe I could even work for one of you someday. If you'd like to get in touch with me, my email address is right up there. About the picture that you see up there, it actually has nothing to do with the talk, but it's a pretty visually boring talk. I like to use my own photography in the talk, and I don't have any photographs that say array of integers or Fortran compiler, so I just use some kind of random photos. So I just threw that up there to make it look pretty. So why do we want to talk about getting Python to talk to these foreign languages? Well, it's one of Python's strengths is its ability to talk to C and C++ and so forth. And I imagine that as largely data scientists that you're interested sometimes in getting Python to speed up, and so you might want to use some compiled code for that. Or oftentimes you might have maybe like a scientific instrument that only speaks to C and doesn't speak to Python, and so you want Python to be able to get it to talk to C for that reason. So Python is actually pretty good at this, but you have a number of options, and also the options have changed over the years. What used to be fashionable, the good ways to do this, are not so good anymore. There are a lot of tools actually out there now to make life a lot easier, and so that the things you may have known about this 5 or 10 years ago are less applicable. And so what I would like to do is just provide some more clarity about the situation and hopefully give you a better roadmap or some ideas about how you can go forward with that. All the choices make this a little bit cloudy and mysterious, which is my excuse to throw in just one more photograph. It's actually some walking into some clouds. It's not a scene from The Hobbit. It's actually my mom and brother in a rainforest in Costa Rica. And it's maybe not a good photograph because that was actually pretty nice, kind of cloudy. And the kind of cloudy I was talking about was bad kind of cloudy, so just forget about that slide then. So the roadmap for going forward, I wanted to cover these topics in the talk. And like any good C programmer, I'm starting from zero by most of my counting. So the first thing I want to cover is just the basic principles of how Python can talk to C and why it's pretty easy for Python to talk to C, and also how those concepts extend to Fortran and C++. And then also talk about the three options you have for getting Python to talk to one of these foreign languages. When I say foreign languages, by the way, I'm talking about the three I mentioned there, C, Fortran, and C++. It's just wordy to say, so I'll call them foreign languages. And then I want to suggest some tools that you might want to use to do this that will help you along your path. And I'm going to try to leave about 10 minutes at the end for Q&A. It might be a little tight. But of course, I'll be here at the conference, and we're going to break for lunch right after this, so you can grab me at lunch if you want to talk to me, or email me at the address, which I'll show again on the last slide. So without further ado, then, let's talk about Python's C API. So when I talk about Python, the Python that's been around for a very long time, and actually was the only Python for a long time, is written in C. In recent years, people have come up with some other Python implementations, like Jython, you may have heard of, is Python written to run against the Java virtual machine. There's also PyPy, which is written in its own particular language and has its own pretty interesting features. The Python we're going to talk about today is only the traditional mainstream Python written in C. The stuff I have to say today doesn't apply to these other Pythons. And if you're not really sure which Python you're using CPython, because you definitely have to go through some effort to use the other Pythons. So this CPython has at its core a C API, and you might have seen APIs before that expose maybe some of the concepts in a language or a package. This isn't that kind of C API. This isn't some half-baked C API. This is a really full-fledged C API that exposes all of Python's inner concepts to anybody with a C compiler. It's actually the calls that Python itself uses to run your Python script. So when you type run myscript.py. Python parses that, compiles it to bytecode, and then calls this C API to do all the things that it needs to do, create lists and dictionaries and functions. This API is pretty stable, obviously changes a bit from version to version. It's well documented. There's a bazillion examples out there for it. And so it's good to know that that API is there. And I want to show you an example of what this API looks like. So up at the top there, we have some Python code for creating a new dictionary. And then at the bottom, we have the more or less equivalent C API function to do the same thing. I don't want to get too bogged down in the details, just to point out that that API is there and to compare the two. Obviously, the code on the bottom is much more verbose. C involves a whole lot more bookkeeping and memory management and so forth. And it's also worth pointing out that C is a procedural language and Python is an object-oriented language. So you have to do some work in C to represent objects, even though C doesn't really have the object concept. So the code at the bottom, I think anybody looking at that, you would compare the two, and you can see that the code on the bottom is much more elegant and expressive and readable. Some people, for whatever reason, still prefer the code on the top. I don't know why. There's just no accounting for taste. But that's what the C API looks like. It is pretty tedious to get code done in the C API, but you can certainly do it. I'm not really going to recommend that you go out and learn the C API. It's interesting. I wouldn't discourage you from it, but you don't actually have to look at any of that if you don't want to. But it's really good to know that it's there and to be aware of it and to understand that that's how Python gets a lot of its work done when it's talking to foreign languages. So now that we know that Python has this C API underneath, you can kind of understand how it's easy for Python to talk to C, right? That it has the C API, so it's pretty easy to get to compile your C code to talk to that API. So what about Fortran and C++? Well, Fortran maps to C reasonably well because Fortran has a lot of the same primitives, right? Fortran has integers and floats and arrays and strings and pointers and so forth, as does C. So Fortran also has a concept called the ISO-C binding, which was added to the standard in 2003. I don't remember. I'm not a Fortran guy in particular, but the ISO-C binding helps Fortran code look even more like C to the compiler, which eases the transition if you're trying to get Python to talk to something. You want your Fortran code to look like C. So it's not too hard, actually, to get Python to talk to Fortran. C++ is kind of another matter because C++ has, of course, the basic C primitives, but the stuff that makes C++ interesting is all the other stuff, the objects, the template library, the exceptions that it has, and so forth. And so managing C++ can be kind of difficult because Python, of course, is a C API, and you're trying to talk to an object-oriented language that exposes all sorts of concepts that C doesn't know about. Python might understand objects and exceptions, but C doesn't. So it's a good bit more work to get Python to talk to C++, but definitely possible. So our three choices then for getting Python to talk to these foreign languages is you can wrap code, you can write an extension, or you can embed Python in an existing executable. And I will go over what each of these mean, but these are really your only three choices. So wrapping is the most common option for people. So wrapping is when you take an existing library, a library that already works, is written in, say, for instance, C, and you want to expose what that library has to offer to Python. So what you do is you create a Python-friendly layer or wrapper or binding, all of those terms mean roughly the same, for an existing library. You write some code that makes the objects in this library or functions in the library accessible to Python. That wrapper can be written in a number of different languages. It can be written in Python or in C, and it has two jobs. First, it wants to do a binary translation of information. So for instance, if you have a Python integer and you want to pass that over to, say, your C library, the wrapper has to translate that Python integer, which is called a boxed integer. It's a special, fairly complicated entity, over to C, which has a very simple concept of what an integer is. Similarly, when you pass information back, it has to be translated from a C concept to a Python concept, or a Fortran concept to a Python concept. The other job that the wrapper has is an idiomatic translation. The binary translation is maybe the harder part. If you screw that up, that's where you get seg faults. The idiomatic translation is really optional, and it gives you a lot more choices as to whether or not you want to work with the idioms of the particular language. So if you think about, you've got this core library written maybe in C or something like that, and it's got a number of features. A really, really thin wrapper is going to wrap over that like saran wrap, or if you're from the UK, cling film. It's going to adhere to the surface and expose all the bumps and crevices and nooks and crannies, and it's going to be the features of the underlying library are going to come through very clearly in Python. A thicker wrapper can actually change the idiom to something from what the core library is written in to something more Pythonic. So if I could give you an example of this, if you look at the code at the top there, that's the documentation for some imaginary library, and you can tell right away what the underlying library is written in. It's in C++, because that's a C++ idiom coming through into your Python code. It's not the end of the world. You can use it. It's just not as nice. The bottom version is a more Pythonic example of the same code, and that means that the wrapper author took more time to write that wrapper and make a nicer wrapper. It didn't take a whole lot more time, but it's a difference. It shows how the two different idioms can be expressed in Python, and the bottom one is nicer. Another diagrammatic way of looking at this, if that's even a word, is to show here how in this core C library that I have maybe, I don't know, 20 functions, and if you write a very thin wrapper, they're just going to come through one-to-one and be exposed into Python without any sort of decoration or fanciness. A thicker wrapper might take the time to translate those concepts, maybe even into objects. If you've got 20 functions, a thicker wrapper might say, you know what, I can group these into 3 categories and express them as objects, which are much nicer to use in Python, or at least they take advantage of some of Python's strengths. So that's what a thicker wrapper could do for you, is make a nicer to use library. There's no right or wrong choice about a thin or a thick wrapper. It depends on how much time you want to spend using it, how much time you want to spend writing it, and how much time you'll think you'll be using it. So wrapping is useful when you have an existing library that already works, and you want to use it from Python, and you don't, or for whatever reason, can't modify the existing code. You just want to wrap it. Our second choice is writing an extension library or an extension module. Extending Python sounds like you might be adding new keywords or syntax. That's not the case. This is actually not that fancy. Probably everybody in here has written a Python module that they then import into their main code. So you say import my module, and then you, through the my module namespace, you have access to all of my modules, functions and objects and so forth. This is the same concept. You're just writing that module in a language that's not Python. So you're writing it in C, but after you get done, you build this module, you can import my module, and it'll look just like a Python written module. The main difference between this and wrapping, or the main differences, is that generally this library is only going to be accessible to Python. It's not going to be accessible through C or C++ or whatever. There's some exceptions to that, but that's the general case. And in addition, an extended library is sort of self-contained. So if you imagine before, when I talked about the wrapper, you have a wrapper around a core library, and if you take away that core library, if it gets uninstalled or changed or deleted or something, the wrapper has nothing to talk to, so it will break. Whereas an extension library is self-contained. It's its own little file. It, of course, talks to the operating system into Python, but it's an entity unto itself. So running an extension module is useful when you need the features of a foreign language, like speed, or as I said before, talking to a scientific instrument or something like that. And you don't need your code to talk to anything but Python. The last topic, or the last way I wanted to talk about, the last technique for getting Python to talk to foreign language code, is by embedding. And embedding is an uncommon option, but it's an interesting one. So what it does is, during the linking step, when you're building your code, it actually pulls a Python interpreter into your executable. So say you have a C or Fortran executable, you link in a Python interpreter, and at some initialization point in your code, you initialize the Python interpreter, and then boom, you have a Python interpreter running in your process space. Well, why would you want to do that? Well, you can call Python code very efficiently and exchange data with it. You can also, for instance, from a C program, shell out to Python, run a Python script from the command line, but that takes a long time. You have to invoke the interpreter, you have to process data through standard in and standard out. This is a technique that allows you to have a Python interpreter in the same process space as your main code. It's useful when you want your foreign language code to call Python. So the first two techniques I talked about, wrapping and running an extension library, they allow Python to talk to foreign languages. Embedding does the reverse. It allows your foreign languages to talk to Python. So it's also an interesting to do if you have maybe a really big application that wants a scripting language in it. You can actually have Python as a scripting language in your application and talk to your native objects. Pretty cool. So as I said, it's a bit unusual, but it's a pretty interesting option. So those are the three techniques: the wrapping, writing an extension module, and embedding. Those are the three techniques that you have for getting Python to talk to foreign language libraries. I wanted to talk now about some tools that can help you execute whichever one of these steps is appropriate for your use case. So the first tool I wanted to talk about is C-types. It's from the Python standard library. So I think some people might think of C-types as an unusual choice because it's a really lightweight tool. It doesn't do a whole lot for you. But one of the things I like about it is that it's accessible if you already have Python installed. You don't need a compiler, you don't need to install anything else, it's just right there. And it's easy to experiment with. And I think that if you're maybe just getting started and you want to try out some simple code, it's kind of fun to work with C-types and just to see what it's like to write a C-types interface to talk to a C function or a Fortran function. So the idea is that C-types gives you some support for creating integers and strings and whatnot that will be acceptable to C, that you can pass directly to a C function and that C will accept, and also to interpret whatever C or Fortran or what have you might pass back to you. One of the things that it does not offer is any automation support. And by that I mean, suppose you have a C library with 500 functions in it. Well, writing the C-types interface to each one of these 500 functions is going to take you a long time. It's going to be really tedious and would probably make C-types not at all an option for that. So I found C-types Gen up there that claims to automatically create C-types interfaces for you. I haven't used it, but it looks like an interesting option. Another knock against C-types is that it doesn't have any C++ support. I want to give a quick example of how C-types can talk to Fortran. There's a very simple hello world written up there in Fortran, and down at the bottom you see the C-types code that you might call that with. You can see the C-types code is a little gunky there. You know, you've got to create a Python variable and then a Fortran friendly variable that shadows the Python variable. And when you pass it, you have to be careful to pass by reference, not by value, because that's how Fortran expects things to be passed to it. You can actually pass the 5 directly by value if you want, and then Fortran will try to access the memory location 5, which is unlikely to work under any circumstances. So you get a seg fault usually. Here's a nicer example based on the previous one with some small modifications. That's the ISOC binding stuff that I mentioned earlier. It just gives some hints to the Fortran compiler that says, you know what, actually I want this passed by value as a simple integer. And then the C-types code is a lot nicer. You can just pass a value directly by, or pass your variable directly by value. So it depends. Neither one of these is right or wrong. If you might want to write a wrapper for your Fortran code or make nicer Fortran code, you can make your C-types code easier. The last example I want to show, not to overdo C-types here, but just a general concept that you might run into when you're trying to move variables around. There's no, this is all Fortran code, there's no C-types up here, but it just shows a general concept of what if you want to move some complex numbers around. Well, Fortran understands complex numbers, and Python understands complex numbers. Unfortunately, the C-types part in the middle does not speak complex numbers. So in order to move complex numbers between these two, what you can do is split them up into their real imaginary parts, send those arrays over to Fortran, and then the Fortran code will knit them back together into complex numbers. Call this function do something, which we don't know what it does. It does some operation on the complex numbers, and then at the end, you stitch the real and imaginary numbers back into complex that make them accessible back into the Python code. Not that exciting or sexy, but it does give you an idea that a little bit of creativity might go a long way towards making things accessible across these language barriers. So that was C-types. It's a good thing to start off with. It's a good simple tool to try things with. Some other tools that are probably more robust and more enterprise ready or whatever you want to call that. There's CFFI, which is a third-party project that interprets C declarations. So you can give it a whole header file and just say, here, go figure out what interface I need for these functions, which is really nice, right? Because that means you're not writing these all by yourself, one by one. It doesn't support Fortran or C++, unfortunately, so it's good at C, not so much for anything else. There's also F2Py, which used to be an independent third-party project. It has since been subsumed into Fortran, or into NumPy. Sorry about that. I looked over it. I haven't used it personally. I looked over it, and it seems to have actually a really nice feature set. It looks like a very interesting project. And so I started Googling around for conversations to see what people were saying about it. And I found almost no conversations whatsoever, which really surprised me. And so my guess is either that it works so well that nobody needs to talk about it, or that nobody uses it. I hope it's the former, because it seems like a pretty neat project. If anybody has experience with that, personal experience, good or bad, I'd love to hear from you in the Q&A section or just at lunch or something. So let's talk about wrapping C++, because as I said before, C++ is a good bit more complex. And one of the main tools for wrapping C++ is Swig, that you've probably heard of before. Swig stands for Simplified Wrapper and Interface Generator, and it can parse C and C++ headers, once again like CFFI. So you can take an existing project and say, hey Swig, here's my headers, you go figure it out, you go build interfaces for this. As I said before, C++ is a lot more complicated than C and Fortran, and so there's a lot more things that can go wrong. Swig has a domain-specific language with which it describes interfaces. So you have these interface files that Swig creates, and if Swig isn't entirely understanding what you're trying to say or what your classes are trying to do, you can modify these interface files to give Swig some more hints. So I call Swig ambitious because what it tries to do is a lot. It says it claims that you can give it a whole C++ project and it will figure out your interfaces for you and build wrappers and hopefully you won't need to touch them. There's a lot of magic involved there because it's inferring things about your classes and moving data back and forth across interesting boundaries. And it's really wonderful when it works because it saves you so much work. However, it's also a little dangerous because it has to make some assumptions that are not necessarily entirely clear. And for instance, there's some memory management differences. The C++ is a language that works with explicit allocation and delete, setting aside smart pointers for the moment. In C++, you allocate and free things explicitly. Python is garbage collected. Python has no explicit alloc and free. And so you can run into problems where Swig is trying to figure out how it needs to deallocate objects and not leave them hanging around in memory. And if it gets those guesses wrong, you get some weird seg fault when you access some memory that's been released when it shouldn't have been. That can be pretty hard to debug. And that means you have to dig into Swig's interfaces, and that can get a little messy. So I think that Swig is good for getting you a lot of the way there quickly, but finishing that last chunk to make everything perfect and beautiful can be kind of time consuming because it's a little difficult to debug. It's a really great choice for large C++ projects because there's nothing else that I'm aware of that can get you started as quickly. Another option for wrapping C++ that I feel like I really have to mention is boost.python. I haven't used this either. I think I helped rip it out of one project. Boost.python seems to have a lot less traction than Swig for whatever reason. And when I Googled around to see what people were saying about it, what I found is a lot of people that kind of dismissed it, too hard, too difficult, but it had a number of people that were really just had glowing reports about Boost.python, some really ardent admirers. And I felt like I would be giving it short shrift if I didn't at least acknowledge it and say that it's out there. And for some people, it seems to be fantastic. My guess is those people are really good at C++ and can appreciate what Boost.Python has to offer. So the last thing I want to talk about is Python, and maybe some of you who know this space a little bit have been wondering when I would get to this. The reason that I saved it until last is because talking about everything else before this makes it easier to explain Python and describe what it does. So Python is both a project and a language. I think the project preceded the language. The language is actually 99% like Python, or it attempts to be a perfect superset of Python. It's not quite. It supports almost all of Python, probably all of the Python you're going to use. And it actually adds on some extra C-like keywords to help you give hints to the compiler as to what your code is doing, and that can add a lot of speed to it. So I call it Python with C sauce. Python is really versatile. It can help you with wrapping, it can help you with writing an extension module, and it can help you with embedding your code. It's the only tool that I'm aware of that can do even two of these, let alone all three of them. So it's really powerful that way. It's also really nice to work with if you're new to it, because it can take straight Python code as its input. And what it does is you give it Python code or slightly modified Python code that has become Python code, and it compiles it. It parses your code and compiles it, quote unquote, to C. So the output file of the first Python process is a C file. And then you compile that C file in a regular old C compiler, and then you have more or less Python code running with a big speed boost, running closer to the executable speed of C. And the nice thing is Python can, of course, do all this in one step for you if you like. And what it's using is, you remember that C API that we talked about on slide 4, or wherever that was? That's what Python is doing, is cooking your Python code down to that C API and then compiling that C API directly. So Python has some other nice features, is that it knows about NumPy, because it knows that its target audience is probably folks like you who are doing a lot of numeric code, and without being able to talk to NumPy, it would be not such a useful tool. So it has support in there for NumPy. It also has decent C++ support, allowing you to move objects across the foreign language boundary. In addition, I wanted to talk about Fortran, because that's part of the topic here. And Fortran90.org has a really nice tutorial on getting Python to talk to Fortran. So that's really helpful to have out there for you Fortran folks in the audience. So one of the knocks against Python is that there's no automated interface generation. So I mentioned before about a couple of tools, CFFI and Swig, can both take a big batch of header files and build interfaces for you. So if you have that function or that library I mentioned before that has 500 functions in it, you don't want to have to handwrite interfaces to each one of them. So that's something that the other tools have that Python does not have yet. There is a project out there called Xdress that attempts to do this very thing, to build automated interfaces for you using Python. Xdress has been, when I last checked maybe a week ago, has had no activity for about 1 year, I think almost to the day, like 1 year and a day or something like that. So it's at that phase of projects where it's had some interest and energy, and now it's starting to fade and get a little dusty. Not at all too late for it to be rescued. And the good news is that the author is right here at this very conference, Dr. Anthony Skopats. He is giving a keynote. So if you're interested in Python and generating automated interfaces, here's your opportunity. I suggest you go talk to him before or after his keynote, maybe even during his keynote. Just interrupt with a question about Xdress. I'm sure he'd appreciate that. So I think we are about out of slides, and that's fine, because I wanted to leave time for Q&A here. So let me go over what I just talked about. So CPython has that C API, and even if you don't use it directly or personally, it's good to be aware that it's there and what it's doing for you and how much it can do. So even if you don't use it directly, it's there, and it's your friend. The three options you have for getting Python to talk to foreign language code are wrapping, writing an extension library, and embedding. All of these can be done without any tools other than a text editor and a compiler. You can do all these by hand with the C API if you want, and for many years that was how people did things. So you don't need any tools, but man, they sure help a lot. They can save you an awful lot of time, and they can save you from digging around in that grungy C API that we looked at before. And then the last point I want to make about from the tools section is that Python is so versatile that no matter what you're considering doing, it really at least ought to be in your list of candidate tools that you're considering. In some cases, you can argue that other tools, like for instance, maybe Swig, would be better for you at getting you started. But one of the nice things about Python is because it's so versatile, the time you spend learning how to use Python to, say, wrap an existing library will pay off later when you go to use Python to write an extension module. So an investment in Python is likely to pay off over and over again down the road. So that was about all I had. I wanted to show you one more lovely picture that has nothing to do with the talk. And thank you. I'd like to thank each and every one of you, but there's not time. So I'll just say thank you, and thanks to our hosts here at PyData. And I did manage to leave about 9 minutes for Q&A. So if anybody has questions, the man with the microphone is over there. And it looks like we have a gentleman in the front here.
You were just asking for a comment on F2Py, so this is not a question, but the reason it's not used is because it refers to a version of Fortran that is not widely available or used anymore. It's quite an ancient tool, and it does ship with NumPy. It needs some love. It needs a champion is what it really needs.
There
and
you
so
go. Perhaps that champion is in this room.
There's an opportunity.
All right, looking for a champion. No, I'm not. We have a volunteer. Wonderful. Thank you. That was easy.
Champion volunteer.
I'm going to have to pass on that one. I have a question, which is, what about, do you have any comment about, everything you've said and wrapping along with other high-level languages? So like, let's say you're working with Python and R, and not just going up to Python, but going up to other high-level languages. Do you have any comments or experience on that?
I honestly do not. You caught me flat-footed. I really don't. I don't know enough about R to really comment on that. I know that Swig has a lot of facilities for producing wrappers for languages other than Python, and that might be able to help you out. But no, I really can't answer your question. I think Mark might be able to. No? You'd have a question to ask. Eric, the gentleman in the front here, has a question. Sorry, I couldn't answer that a little bit better.
Are part of the interface problems when you're talking about marshaling back and forth data, simple like an integer, does it include the byte order, low order byte first, high order byte first, or is it just that much more complicated?
No, the moving simple things back and forth like integers are generally not a problem. It's, well, say if you're talking to Fortran, you have to be aware that, for instance, its arrays are column major instead of row major and things like that, and strings are terminated differently and so forth. And then it gets even more complex, of course, when you're talking about C++ and moving objects around. So no, byte order is not a problem. Sometimes size of an integer, 32 versus 64-bit. The first Fortran example I showed up there was really sloppy and made some assumptions about sizes of integers, and let's try it out. It might work. If you get a seg fault, then oops, maybe you need to investigate. But yeah, it partly depends on what you're trying to pass across and what you're wrapping. It gets complicated as you go up. Gentleman in the... I saw this guy first. I'm not sure who...
So tell me about deploying stuff you've written with Python, basically, because it seems a little complicated. It's got to go through a multi-step process. Can someone come along and like pip install something that was written using Python?
Yes, and so it's a really interesting question about deployment. The good news is that Python wheels have rescued us from a lot of deployment problems, so you can deploy binaries much more easily. And It's a bit more complicated if you're trying to pass it along Python C code. So one of the really nice things about Python is that if you have a C compiler already installed, you can write your setup.py to accept Python C files, and they'll get compiled on the fly pretty easily with not much fuss to the user. It's a lot harder if you're deploying to, say, for instance, Windows, where people don't tend to have a compiler installed, and it's a big project for them to get one. If you're deploying to, say, a Linux environment where you know there's compilers readily accessible, deploying Python, even if it's not precompiled, is pretty easy. Was there another question out there? There was a hand up there somewhere.
Hey, for the embedded side, how do external packages work? So if you were to embed a Python interpreter, how do you natively get the NumPy and pandas and all that other stuff? Is that an easy process, or is it a manual?
It's easy once you do things right. So what at the beginning, when you initialize Python, you tell Python where it can find its libraries. And so you need to provide, in addition to your embedded Python, the Python standard library, because of course a lot of Python is implemented in Python itself. And so just embedding a Python interpreter into your executable doesn't actually get you fully fledged Python. You have to provide the Python runtime library and also the Python standard library. And in with that standard library, then you can supply all the other good things that you usually find in site packages, NumPy and whatever you like. But so it can be a little bit of an adventure trying to get embedded Python to find the right libraries. But once you do, you're good to go. A good question. Well, I guess there are maybe no more questions or comments. So I just want to thank you all very much again. And if you have any questions for me, maybe I'll see you at lunch. So thanks again. Enjoy the rest of the conference.